All right, welcome to the next lesson, which is going to go to section 1.4. There are two things we're going to talk about in this section, and those are continuity and also what we call the intermediate value theorem. So for as far as something being continuous, okay, here's a graph. Notice I drew it, and I didn't have to lift up my chalk or your pencil when you're writing this down. You just draw one smooth curve, right? Intuitively, that's what we mean by something being continuous, okay? Versus something like this, so this is continuous. So let's say I do something like that, and then I stop here, put a hole, lift up my chalk, and then I go something like this, okay? That is something, that's an example of a graph or a function that's not continuous, okay? Now we're going to formally define what it means to be continuous, all right? So here's the definition. We say a function is continuous at a value x equals c if three things happen. Number one, f of c is defined. In other words, if you just plug in the c value, your function gives you an answer. Okay, that's number one. Number two, the limit as x approaches c for f of x has to exist. Okay, and the third thing is we kind of merge these two together. We say that the limit as x approaches c of f of x is exactly the value that you would get when you plug c into the function. Okay? And we'll kind of explore that in a little bit with an example. But now this begs the question, so if this is what it means to be continuous, right? This is not continuous. First example, nice and smooth, continuous, didn't have to lift up the pen or the pencil or chalk in my case. This example here, notice there's a gap or a separation, okay, and I had to physically lift up my chalk to draw the second part of the graph. That's not continuous, okay? So let's talk about what that looks like specifically, because there's a few different kinds of functions that are not continuous, or in other words, we say discontinuities. So these are now types of discontinuities. Okay, and there's really three. There's two types, but there's three total. The first is a removable discontinuity. So that's one type. The second type is non-removable. Oops, I meant to do yellow. Okay, and now graphs that simply have a hole and nothing else. So smooth graph and then hole, and then we just kind of pick up right where we left off. That's a removable discontinuity. It's called a hole. And so that would look something like this. Moving along, hole, and we just continue. Okay? So this would be a removable discontinuity. And now the two types of non-removable, we have graphs that have vertical asymptotes, and then also graphs that have what we call a jump discontinuity. Okay? So graphs that have vertical asymptotes look something like this. Notice that I have to lift up my pencil to draw both parts of this graph here, okay? And a jump discontinuity, we've actually seen a few of these already as well. That's where we are graphing, and then there's a hole, and then we jump to a different value at that x value. So either we go up or down something. And so something like this, where we jump from the hole to the next part of the graph, that's what we call a jump discontinuity. Okay, so those are the three types of discontinuities that you have to know. All right, and now let's look at an example about how we can determine if a function is continuous or not just intuitively, but also using the definition here. Okay, so let's have this example here. Is g of x equal to the piecewise function, the square root of 2 minus x, if x is less than 2, and then the second piece of the graph is going to be 2x minus 4 if x is greater or equal to 2, continuous. Okay? So let's just kind of go through, let's do by definition first. Remember, these are the three conditions that need to be met. So first of all, and I should say continuous at, well, yeah, just continuous. Don't need to say specifically at what value, but what I was getting to is that here's where the issue is going to be, right? Well, anytime we have a piecewise graph, that means we could potentially have something like this where we graph part 1, and then there's a separation or a jump, and then we pick up and graph the second part of the graph. And that's what we're trying to avoid. Okay, but just going through each of these conditions, number 1, so this is where the issue is going to be, right? What's f of 2? If I plug 2 in, according to this graph, I follow the square root of 2 minus x if I'm using values that are smaller than 2, which is actually what I'm doing, or take that back, which is not what I'm doing. Here I follow 2x minus 4 if I'm using values that are 2 or higher, which is exactly what I'm doing here. I'm plugging 2 in, right? So I just follow this, and you do get a value. It's defined, so part 1 is complete, okay? 2, now we have to show that the limit exists, okay? Well, if you take a look at the graph, okay, when we graph the square root of 2 minus x, this is a graph that's been flipped across the y-axis and shifted to the right 2. And so that's going to be something like this. Okay? But now, the second part of the graph, 2x minus 4, that would be y-intercept of negative 4, slope of 2, so I'd go up 2 over 1. But I don't want to start graphing until I reach 2 and onward, right? Because that's what that says for the second part of the graph. Notice that I actually end up landing right on top of this point that I already have. And for completeness sakes, I kind of messed that up. This should have been an open circle to start, right? Because we don't include it on the first part. But because I include it in the second part of the graph, I end up filling it in, and then I continue up 2 over 1 for the slope, and now we get something that looks like that. All right? And so according to this, the limit as x approaches 2 for g of x does in fact equal 0, right? From the left, I get to y equals 0, and from the right, I get to y equals 0. I go to the same point, okay? So that's the second condition. So the limit exists, there it is. Third condition, not only does this limit exist, this limit actually has the same value as the function. So now we can say that the limit as x approaches 2 for g of x equals 0, which also happens to be the value for f of 2. Okay? And so for these three reasons, f of 2 is defined, the limit at 2 exists, it's equal to 0, and those match, that's the third condition, then we can say g of x is continuous. Now, intuitively, could you draw this graph without lifting up your pen or paper, or pen or pencil? Right, so here we go. Ignoring the arrows, right, but can we just do this? Absolutely, right? No problem drawing that in at all. Okay, so continuous intuitively, continuous by meeting the three conditions that we've established. Okay, so notice that these two end up producing 0 when x is 2. Okay, so that's kind of a good hint for this problem. Find a such that the function f of x equals negative 5a squared x if x is less than or equal to 1, and 3ax minus 2 if x is greater than 1. Find a so that f of x is continuous. Okay, so clearly the issue is going to be at x equals 1. Everywhere else we're all right, but at x equals 1 we might have a problem, but in order to have something like this where there is no issue with continuity, these two functions need to produce the same exact output at x equals 1. Okay, so f of x has to equal negative 5a squared x, which has to also equal 3ax minus 2 at this location where we have that separation, potentially. We're trying to fix it so that there is no separation there. And so as long as these are equal, then we can figure out how to make that work. Now, since I know x has to be 1, okay, I can just plug 1 in. So I get negative 5a squared. That's just going to be 3a minus 2. All right, and now we're just going to solve this equation. So this is a quadratic. We're going to set it equal to 0. So move the 5a squared to the right. And you should be pretty comfortable factoring quadratic trinomials. Let's see, this has to be 5a times a. We need to have a 2 and a 1, but I think it's going to go something like this, right? This is going to be 5a, that's 2a, make that a plus, make that a minus, we should be good to go. And now, zero product property, we set both of these factors equal to 0. So you get a equals 2/5 or negative 1. So either one of those values, so if I change that to a 2/5 in there and in there, or if I change that to a negative 1 and a negative 1 in the second piece, you're going to get a continuous graph. Okay? All right. And the last part of this section is the intermediate value theorem. So we've kind of talked about continuity, what it means graphically, what does it look like, and then also the specific conditions that need to be met and how to verify them. Now we're going to end with the intermediate value theorem, IVT for short. And here's the setup. So let's say we have a graph. between A and B. And so let's say this is f of x. We're only looking between A and B now. Okay. This has a coordinate, a y value of f of b. This over here has a coordinate, a y coordinate of f of a, this location there. Okay? And so here is the intermediate value theorem. If f of x is continuous, and change that. If f of x is continuous on the interval from a to b, and k is between f of a and f of b, so somewhere in between these two y values, we have a k value right there, okay? Then there exists a c value in the interval from a to b such that f of c equals k, okay? It actually is pretty common sense, okay? If we have a continuous graph from this value to this value, and in between the two, the starting value and the ending value of f of x, we have some other value, k. This is saying, well, this function has to hit this value k at some point. If it's continuous, it can't skip over k. It's got to go through that value. And so therefore, we know that f of c will exist and its value output would be k. All right? And so here's kind of how you would use that. So given f of x equals 2x to the fourth minus 6x cubed plus 2x minus 3 show that f of x has a 0 in the interval from -3 to 1. Okay, so how do we verify or show that we're going to hit 0 be somewhere between -3 and 1? Okay, so first what we're going to do is find out what these boundaries are. So if my left boundary is -3 and my right boundary is 1, I'm going to plug that in. So f of -3, okay, if you go ahead and calculate that, that'll be 2 times -3 to the fourth minus 6 times -3 cubed plus 2 times -3 minus 3. Okay, when you calculate all that, you get 315. And now if you calculate f of 1, plug in 1, so that's 2 times 1 to the fourth minus 6 times 1 cubed plus 2 times 1 minus 3. That's going to be equal to -5. Okay? So what does that mean? So if I think of the picture, at -3, my function has an output all the way up at 315, somewhere up there, right? And now at f of 1, my output is -5. Or at 1, my output is -5, okay? To get from this point to this point, if this graph is continuous, it's got to hit the x-axis at some point. There's no doubt about it. It might look something like this. It might look something like that. It might just be a straight line. It doesn't really matter. At some point, it's going to hit the x-axis, which is what we mean by having a 0. It could have multiple. It could also do something like this, right? It could have multiple zeros, in this case 3. But all we're asked to do is explain why there has to be at least one c value in that interval, and I think we've done it. So let's just kind of recap it, okay? So here's the explanation. F of x is continuous on the interval from -1 to 3, since it's just a polynomial. All polynomials are continuous everywhere. Okay, so that's number 1. And now since we calculated f of -3, and that was equal to 315, we also calculated f of 1, and that was equal to -5. Oh, I think I erased, I must have erased it. This was equal to -5. Okay, so since I calculated both, and I have one positive and one negative value, okay, there must be a 0. Because we know -5 is less than 0, which is less than 315. In other words, 0 is between -5 and 315. So that guarantees that we have to go through that value at some point. Okay? And so that is the end. I hope that this made some sense and that I actually got the entire recording because my computer went on standby. But okay, it looks like we're good. All right, so that is it for now. We'll see you next time.